PhD student at the CS department of Princeton University. And before that, he completed his undergrad degree at the Yale class in Tsinghua University. And he has already made, sorry about the siren. He has already made very interesting contributions to multiple areas of machine learning, including reinforcement learning and minimax optimization. And without overdue, Yuanhao, please take it away.
Yeah, thanks for the nice introduction, and it's really great to be here. So today I'm going to talk about a recent work on an exponential lower bound for MDPs that satisfy linear realizability and a constant suboptimality gap. So this is a joint work with Ruosong Wang and Sham Kakade. So now let us first quickly go over some standard concepts in MDPs. We have a state space S, an action space A, and for every state action pair, we assign the reward and a distribution for the next states. In this work, we consider episodic reinforcement learning. So we start from a state S1, take the action A1, observe the reward, and go to the next state until the edge time step. And that is one trajectory for every episode. So we'll define the value function and Q function in the undiscounted episodic way as well. And as we all know, the goal of reinforcement learning is to find the optimum policy which maximizes the value function. And today we're talking about linear function approximation. And the reason to consider function approximation is that doing things in a tabular way, then dealing with large state spaces is hard. And in particular, the sample complexity for finding a good policy is lower bounded by the size of the state space. And this is undesirable for applications like chess or Go, where the state can be 10 to the hundreds. So in the case of function approximation, instead of treating these states and actions as tabular objects, we have a feature extractor that hopefully is informative about them and can help us reduce the sample complexity and get rid of this dependence on the size of the state space. So in the special case of linear function approximation, we will try to use the linear function phi SA transpose theta to approximate the Q function. And the reason to consider linear functions is that linear functions are simple, and we already know how to deal with them in contextual bandits. So now a natural question to ask is, when is reinforcement learning in the linear function approximation setting tractable in a statistical sense? So in the theoretical perspective, the way to ask this question is, under what kind of assumptions can we prove a good sample complexity upper bound? So here are a few assumptions that appear in existing literature. So the first one of them is realizability, where we assume that the optimal Q function, Q star, can be written as the linear function phi SA transpose theta star for some parameter theta star for every state in action. This is a very natural assumption to consider if you use value-based methods, because in these algorithms, you are exactly trying to learn this optimal Q star. And it is also one of the weakest assumptions compared to the other assumptions that are used in the RL theory literature. However, there is a recent negative result by Weiss et al., which says that realizability alone is not sufficient to prove efficient RL. One thing to note about this lower bound is that in the hard instance constructed by Weiss et al., the feature vectors would shrink by every time step. So at the end of the episode, the feature vectors of all state actions are exponentially small. This means that if you try to predict Q star at the end of the episode, you can just predict 0 and get very small error. So in other words, there has to be a mechanism that amplifies this error from a small error at the end to a large error at the beginning of the episode. So some other assumptions that we are going to talk about today include this minimum gap assumption. So in the gap assumption, we assume that for every state, the Q star for the optimal action has a gap between, there's a gap between the Q star of the optimal action and the Q star for any other action. So this is common in multi-arm bandits and tabular reinforcement learning to show instant dependent bounds. But for the function approximation setting, the nice thing about having this gap is that it allows us to identify the optimal action exactly if we learn the Q star function to a precision below a certain threshold. Intuitively, this might help us avoid the error amplification problem. So some other assumptions include stronger assumptions on the feature extractor phi. For instance, MDPs that satisfy Bellman completeness, in MDPs that satisfy Bellman completeness for any theta h plus 1, in the Q function induced by passing theta h plus 1 through the Bellman operator, we assume that this induced function is linear in phi SA for some parameter theta h. So this is a much stronger assumption than realizability because it involves not only the optimal Q function, but also other thetas. And it is known that under this setting, we can find a near optimal policy using polynomial number of samples. And there's another line of work on linear MDPs where the transition kernel has a linear structure. And that is actually can be considered as a special case for the Bellman completeness assumption. And so they can also be done with polynomial sample complexity. Yet another way to strengthen our assumption is by assuming a stronger model of interaction with the environment. So in the standard reinforcement learning setting, we can only follow the actions of an agent. However, in the generative model setting, we can query any state and action pair that we want and observe the reward as well as the net state. This is much stronger than the standard online reinforcement learning setting. And in the work by Du et al., it is shown that if we have realizability and the minimum gaps assumption, as well as access to a generative model, then we can find a near optimal policy in polynomial samples. The basic idea of this procedure is the following. So because we have a generative model, we can query all the features for every time step. So we will do linear regression step by step, starting from the last step. We first query all of the features and compute an optimal G-optimal design on these features. We then query state and actions directly following this G-optimal design and use the collected samples to do a linear regression. Because we have used optimal design, we can guarantee that the estimated Q function is close to the true Q star in infinity norm to a precision that to an arbitrary precision, say delta min over 2. Then by the gap condition, if we follow the greedy policy with respect to this estimated Q, we can guarantee that this greedy policy is exactly the optimal policy. We can then consider this last step solved because we have found the exact optimal policy and continue to the previous time step. So here is a graphical summary of the results that I just mentioned. So first, we know that linear MDPs, as well as MDPs that satisfy Bellman completeness, can be solved in polynomial number of samples. And as well as realizability, as well as under realizability and gap and access to a generative model. On the other hand, we know that from the lower bound, realizability alone is not sufficient to guarantee polynomial sample complexity. And what remains unclear is the setting in between, which is realizability as well as a minimum gap. It is not unreasonable to think that this is doable because with further assumption on the generative model, we can solve it with polynomial number of samples. And also, the gap transition seems quite helpful. However, our lower bound will show that this is actually not the case. And there is an exponential lower bound under these two assumptions. So specifically, we have proved that we can construct an MDP such that both realizability and the constant minimum gap are satisfied. And any algorithm would need an exponential in either D, which is the feature dimension, or H, which is the length of the horizon, to find a good policy.
Yuanhao, can you say a little bit about the size of the action space in your construction, as well as maybe briefly in those prior works?
Okay, so in all of the prior works by polynomial sample complexity, I actually mean without dependence on the number of actions, at least for results contained in this graph. So as for the lower bound construction, the number of actions is indeed exponential in D. So it is this, this number M, if you can see my cursor.
Yeah, we can see your cursor.
Oh, thanks. Does that answer your question? Okay, so there are some implications of our lower bound. So first of all, if you want to achieve polynomial sample complexity, or specifically polynomial without dependence on the number of actions, then we need stronger assumptions than realizability and a minimum gap. And also, we can compare our lower bound with the upper bound that is proved with access to a generative model. So by comparing these two scenarios, we can see that in this case, access to a generative model provides an exponential advantage in terms of statistical efficiency. So although the generative model setting definitely sounds much more powerful, there's little separation results between the two settings, such as this one. So now we'll move on to the construction for the MDP in this case. It is actually largely inspired by the construction in the previous work by Weiss et al. So the first step is to find a set of random vectors that are nearly orthogonal. So to do that, we evoke the famous Johnson-Linus-Strauss theorem, lemma, and we'll choose M to be exponential in gamma squared times D. And the JL lemma guarantees that we can always find M unit vectors such that for any pair, the inner product, that is VI transpose VJ, is at most gamma and at least minus gamma. And we'll choose gamma to be 1/4 for reasons that we'll soon see. The next state is to define the states and the feature map. So we'll have M+1 states in this MDP. The first M states are labeled bar 1, bar 2, and all the way to bar M. And we also have a special state, F, which we'll call the terminal state. As for the action space, we have N-1 actions for every state. And for simplicity, we'll label the actions for the state bar A by 1 to M except for A. This is only a matter of naming the actions and is therefore without loss of generality. Finally, we define the features as follows. For the state bar A1, if we take the action A2, the feature is defined as the inner product of VA1 and VA2 plus 2 gamma times the vector VA2. So this is essentially the vector VA2 scaled with the length VA1 transpose VA2 plus a constant 2 gamma. And as for the terminal state F, we will set the feature to be 0 for all of the actions. Note that here, the construction of the feature is symmetric for all states and actions. So no state or action are special. The third and final step is to define the rewards and the transitions. So to do that, let us first fix a special A star from 1 to n. Then we will construct the transition as follows. If you start from the terminal state F, then regardless of the action that you take, you always receive 0 reward, and you will stay at the terminal state. If you start from a non-terminal state bar A1, and if you take the action A star, you go to the terminal state F with probability of 1, and in the meantime, you will receive a reward that is VA1 transpose VA star plus 2 gamma. Finally, in the case that you take an action that is not A star, there will be 2 possible outcomes. You either go to the state bar A2 with probability VA1 transpose VA2 plus 2 gamma, or go to the terminal state. In the meantime, you receive a reward defined as minus 2 gamma times VA1 transpose VA2 plus 2 gamma. So this defines everything about the MDP except for the final time step. As for the final time step, we will simply set the reward to be the inner product of the feature and the vector VA star. So this concludes the definition for our MDP. Is there any questions so far? Great. So we'll move on to verify that this MDP indeed satisfies both realizability and a constant suboptimality gap. As for realizability, we claim that the Q star for this MDP would be the same as phi SA transpose VA star. So the proof is comes in 3 parts. First, for the terminal state, because we will always stay at the terminal state and receive no reward, the optimal value function is 0. Second, if we start from a non-terminal state bar A1 and take the action A star, then we'll certainly go to the terminal state F and we'll receive a reward. Since the value of the terminal state is 0, the Q star for taking this action A star would be exactly the same as the reward for this action, so which is VA1 transpose VA star plus 2 gamma. So finally, we deal with the case where you start from a non-terminal state and take a action that is different from A star. Recall that in that case, we can either go to, we can either transit to the terminal state F or go to a non-terminal state bar A2. So we'll prove the claim about the Q star and V star of these states through induction on edge. So suppose that we already know the V star function for the next states. Then we can compute the Q star for the state bar A1 of taking the action A2 by plugging in the definition. And through basic arithmetic, we can verify that the Q star for bar A1 for taking the action A2 is indeed the inner product of VA1 and VA2 plus 2 gamma times the inner product of VA2 and VA star. So the point here is that if you compare the expression for the Q value and the definition of the features, then we can find that this is indeed by bar A1 A2 transpose VA star. The final step to compete complete the induction is to show that this action A star is indeed the optimal action, and that V star of bar A1 is equal to Q star of bar A1 A star. So to do that, let us observe that the Q star for bar A1 of taking the action A2 is at most 3 gamma squared, because the first factor here is at most 3 gamma. But the value for taking the optimal action A star is at least gamma. Because of our choice of 1/4, gamma would be larger than 3 gamma squared. So A star would indeed be the optimal action. So combining the 3 claims above would prove realizability. Checking the gap condition is easier because we've already computed the Q star and the V star functions. So at a state bar A1, the Q star function for taking a non-optimal action is at most 3 gamma squared, and the optimal value function is at least gamma. So the gap here is at least gamma minus 3 gamma squared, which is 1/16. Here we ignored the terminal state F for simplicity. But this can be easily fixed by introducing another dimension to create gap at this terminal state. So this sums up the construction of the hard MDP. Here we have n+1 states, and we can verify that it satisfies both realizability and a minimum gap of 1/16.
That's a good question. So in your construction, the discount factor is 1/4, right? Or no, that gamma is not discount factor. It's just an arbitrary. Okay.
Yeah.
All right. So this is a finite horizon. No, yeah. Never mind. No.
Yeah. So gamma is a constant chose as 1/4, and it's supposed to determine how large the gap is. So the gap is here is gamma minus 3 gamma squared. So it's almost of the order gamma. Yeah, and another interesting property of the MDP is that the optimal action is always a star for every state. So finding the optimal policy in this MDP would amount to find this optimal action A star. So now we'll show why this is hard. So recall that we need to find this special action A star. And because we defined in the definition of the feature, you won't find A star. And this is also true for the reward, except for the last step, and except the case where you take A star directly. And also, if you don't take the action A star, the transition probabilities are also independent of A star. So we conclude that in order to receive feedback about A star, our algorithm needs to either take A star or visit a state that is non-terminal at the end of the episode. If the algorithm stays at the terminal state at the end of the episode, the reward that it receives will still be 0. However, the second event happens with very small probability. This is because if we start from any state that is non-terminal, there's always some probability of going to the terminal state, which is at least 0.25. So this happens for every time step. And in the end, the probability of staying at a non-terminal state is at most 0.75 to the edge, regardless of the policy that you use. So this means that in order to receive information about A star with high probability, you have to rely on taking A star itself. This amounts to a needle in a haystack situation, because if you don't take the action A star, with high probability, you can't see any feedback, and you have an exponential number of actions. So we conclude that you need an exponential number of trajectories to find the optimal A star. So this concludes the proof for our lower bound. A lower bound has an additional interesting implication. So suppose that we set up a new feature map for the states called psi. We can set psi such that the V star function for the states would be linear in psi, except for a special state bar A star. So this is in contrast to an upper bound shown recently, that if V star is linear in psi and Q star is linear in phi, then an algorithm can find the optimal policy using polynomial number of samples. So seemingly there's a contradiction between our lower bound and this new upper bound. But actually this can be resolved because there's a subtle difference in the setting. For our lower bound to work, we need to set the feature map at the special state bar A star in a way that reveals information. So our lower bound only works in a case where you can only query the states, where you can only query the features for the state that you're actually in. But the algorithm used in this upper bound implicitly needs to query states that you're not actually visiting. So this difference in setting results in different complexity results. So actually this suggests that in order to find the optimal policy in the linear V star Q star setting, you have to enumerate all of the features, and therefore you have to have a computation cost of at least omega s. So now we move on to a second part where we'll try to prove an upper bound using stronger assumptions than realizability plus gap. So one assumption that has been already considered is called low variance. Under this assumption, for any policy pi, the expectation of the gap between V star and V pi squared would be smaller than C times the square of the expectation of the gap between V star and V pi. So this is essentially the opposite side of Jensen's inequality. The result by Du et al. Shows that if you have realizability and gap and this low variance condition, then you can find a near optimal policy in polynomial number in But here, the polynomial would have a dependence on the number of actions. So in this talk, we'll consider the case where the number of actions can be exponential. So this is not really desirable. Our contribution in terms of the upper bound is twofold. We first removed this dependency on the number of actions in their setting. And we also explored a different assumption that can replace this low variance assumption for proving a good sample efficiency, a sample complexity gap. So let us first revisit the algorithm used by Du et al. It is called distribution shift error checking, or DSEC. I don't really want to go into the details of this algorithm, but the main procedure for the algorithm is called learn level, and it is supposed to learn a certain level edge. So what it does is it comes into 3 blocks. In the first block, it checks for every layer after edge for distribution shifts. And if the algorithm have passed all of these tests, it will try to collect samples at the layer edge in the following way. It first draws an exploration policy from a set of maintained exploration policies and run this policy until reaching SH. Then at the edge layer, it will play an action that is drawn uniformly from all of the actions to perform exploration. Afterwards, it will execute the greedy policy based on the maintained parameters theta h plus 1 to theta bit h. Finally, the label for this sample would be the cumulative reward starting from layer h. After collecting all of these samples, it will compute an estimate for theta at the turn level using ridge regression. It's actually quite easy to see why this algorithm has a dependency on the number of actions. It's because in its exploration scheme, it chooses the action randomly from all of the actions. And that is, so that's actually ignoring the structure provided by the feature map. So what we propose is the following. At a state S, instead of viewing every action as a tabular action, we view it as a vector provided by the feature map. Then we compute the G-optimal design on this set of vectors and sample the action AH from this G-optimal design distribution instead of from a uniform distribution over all of the actions. And this modification is sufficient to remove the dependency on the number of actions. The second thing that we want to do is to replace or relax this low variance assumption. And to do that, we need to first understand why do we need it in the first place. So in the original analysis of the distribution shift error checking algorithm, the argument is presented as an induction. The first claim is that if all of these recursive tests have not failed, the estimation error of Q star using the maintained parameters are small. And we can denote them by delta h plus 1 to delta bit h. So using Markov's bound as well as the gap condition, this implies that if you follow the greedy policy, the probability of not taking an optimal action is actually quite small. And this probability is of the order the sum of all of these deltas over delta min squared. So here delta min is the minimum gap. So now that we know with high probability, the agent is always taking the optimal action by following the greedy policy, we can guarantee that Y is actually a quite good estimate for Q star for most of the time. So we can expect the ridge regression estimator, theta h, to also have a small L2 loss, delta h. But the key question is, how exactly does delta h depend on the error in the later time steps? In particular, if delta h scales as linearly in the summation of the later deltas, then the error will blow up exponentially because it would essentially double by every layer. And that's something that we need to avoid. So the key to resolve this issue is it's actually in the analysis of this question called linear regression with sparse bias. Here we have some samples xi and yi, where y is generated as a linear function of x plus a mean zero noise and a bias that is 0 with high probability. The task is, given a set of such x and y's, how can we estimate theta, the true parameter theta star, such that we have a small L2 loss on the true distribution? Suppose that we get an L2 loss that scales linearly in delta for this problem, then we will suffer from the exponential blow up in error that I just talked about. So what we really want is an L2 loss that is sublinear in delta. But unfortunately, in the worst case, the L2 loss is indeed omega delta. So the worst case scenario is quite simple. Suppose that x is 0 for most of the time, and only it's 1 with probability only delta. And theta can be either 1 or -1. In this case, we can choose this bias B such that the y that you receive is always 0, and your algorithm cannot learn anything. So in this case, if x is 1, then you can't really predict x transpose theta, except for guessing randomly. So the L2 loss that you get would be omega delta. This means that if we do not make additional assumptions, then we'll be stuck with this linear regression problem. This is exactly why the low variance condition is assumed in the original upper bound. So provided, so if the low variance condition holds, then this then the sparsity of B would imply that the expectation of B squared is bounded by C times delta squared instead of delta. So here the assumption basically reduced the variance of B from delta to the order of delta squared. Then by plotting this into the analysis of ridge regression, we can get an L2 loss that scales as delta squared instead of delta. And this will contain the error amplification and avoid the blowup. So if we want to replace this low variance condition, what we really need to do is to find another assumption that allows us to have a sublinear rate for this linear regression with sparse bias problem. So this is very closely related to robust linear regression. And indeed, one assumption that is very useful in robust linear regression would also work for us. And this is called hypercontractivity. So technically, a random variable x is said to be C4 hypercontractive if for any vector v, the fourth moments of x transpose v can be bounded by c times the second moments of x transpose v squared. So again, this is the opposite direction of Jensen's inequality. So there are many distributions that satisfy hypercontractivity with a small c. The list includes Gaussian distributions with any covariance matrices, uniform distributions on hypercubes, and strongly log concave distributions. If we assume that the distribution of x satisfy this hypercontractivity property, then we can indeed get a better rate for this linear regression with bias problem. So suppose that x is C4 hypercontractive, and we use the ordinary least square estimator with polynomial number of samples. We can show that the L2 loss of the estimator scales as delta to the 1.5 instead of O delta. And this is sufficient to suppress the error amplification. So suppose that now we have L2 losses that are smaller than delta for all the later levels. Then at this current level, using this hypercontractivity lemma, we can show that delta H can be bounded by H times delta to the 1.5, which is smaller than delta if delta is small enough. So this hypercontractivity assumption will allow us to contain the error amplification.
Can you say a little bit more about what does it mean in this in the MDP context? Because in the linear regression context, it's clear that it's talking about some property of the distribution of X, right? So
yes.
And then in the RL case, it's talking about some property of the distribution of the states, but under what distribution or on a what policy are we talking about it?
Yes, you're definitely right. So we're essentially essentially what we need to assume that is every time we do linear regression, the distribution that we draw the samples from is hypercontractive.
I see. So I guess the most conservative way to assume it is to say for any policy.
Yeah.
And there's the state distribution. Okay.
Yes. That's actually the laziest version to status. So for any policy, the induced distribution of the features is hypercontractive. So intuitively, hypercontractivity is a sort of anti-concentration property. So you can see that the distributions that satisfy hypercontractivity are very continuous, and the hard cases for hypercontractivity is actually the Bernoulli.
Yeah, I wanted to ask, like, what are examples when hypercontractivity doesn't hold?
Yeah, that's exactly Bernoulli distribution. So suppose that you have x that is 0 with probability 1 minus p, and 1 with probability p. Then on the right-hand side, you have something that scales as c times p squared. But on the left-hand side, on the left-hand side, you have something that scales as p. So c needs to scale as the inverse of p, which can be large if p is very small.
In the context of RL, what would be an example when this like in terms of the features and whatnot? I understand, okay, Bernoulli, just special case, but like the hypercube is also mentioned. So it's like very common maybe that the features take values, I don't know, some hypercube, then some wiki distribution from this perspective would be, it's something that kind of replicates the Bernoulli on each dimension or something. And it's a small, I guess it's like if the parameter can be pushed as small as possible, right? Or something like that. Like it was important that the Bernoulli parameter was going to 0.
Mm-hmm.
I see. And in general, if you have some atomicity, is that a problem, or that's not on its own a problem, right? Like that's not a problem. I mean, like if you have bounded features and like these expectations are just values, like so x is concentrated in a single point, that's totally fine. It is other than that. Mm-hmm.
Yeah, single point distribution is fine, but for a distribution, for say a uniform distribution on k points, in general, C was still as a polynomial of k. So it gets larger as k grows.
Okay, interesting.
Yeah, so the point is that hypercontractivity itself is not very hard to satisfy for these continuous distributions. But in the context of RL, since we need to assume that this holds for any policy, we still don't have a very natural special case. So hopefully we can. So the best scenario is that if your feature distribution is not too discrete and something continuous, then we will have a reasonable C in the hypercontractivity assumption.
Also, you talked about how comparing this with low variance. So I guess you were talking about both assumptions give you sublinear robust linear regression with sublinear in delta error rates. But do these two assumptions like strictly imply one another, or are they still different assumptions?
Yeah, there are two different assumptions. For instance, the low variance condition does not have anything to do with the future map phi. And hypercontractivity does not have very much to do with, say, the optimal policy. So I think there are two distinct, they're not really related. So the thing that they share in common is that they allow us to have a good rate for robust linear regression. Yeah, so to state our result formally, we prove that if you have realizability and a minimum gap, and one of the following, so it's either low variance or hypercontractivity, then you can then the DSET algorithm is able to find a near optimal policy using polynomial number of trajectories. So to sum up,
when you say DSEC algorithm, it's I guess DSEC with optimal design.
Oh yes, that's right. So it's our modified version of DSEC.
Right. Good.
So to wrap up, we have proved two results. On the lower bound side, we've shown that RL is still hard even if you have both realizability and a large suboptimality gap. And on the upper bound side, we've shown that our modified DSET algorithm can find a near optimal policy with polynomial samples if you have realizability and a gap, as well as one of low variance or hypercontractivity. So these two assumptions are used to get a good rate for robust linear regression. So that's the end of my talk. Thank you. Thank you very much for listening. So any questions?
Yeah, so that was actually a question on YouTube, which was about the role of the number of actions, because you were saying that, well, your bounds or your lower bounds are independent on the number of states and actions, but maybe this exponential dependence on D is the dependence on the number of actions in disguise.
Yeah, that's well, there's definitely that possibility, but that does not mean we should have this dependence on the number of actions. For example, for linear bandits, there's no dependence on the number of actions if you treat it with dependence on the dimension.
Right.
I mean, though we have Chaba and I and our students, other collaborators, we have a recent algorithm for generative setting that does have this exponential dependence on actions. So I think it's plausible, but yeah.
Do you mean the paper under the linear V star setting?
Yes. Yeah.
Yeah. I think that's an even larger dependence on A, right? That's exponential in A, and here we have exponential A, so that's doubly exponential. But still, I think the even bigger difference is between linear V star and linear Q star. So, for instance, I don't think there are many hardness results about linear V star, and I don't think that on the other hand, I don't think it's very trivial to extend your algorithm to linear Q star.
So there's also a question on chat. What about the running time of DSET? Is it a polytime?
Yeah, it is polytime. All you need to do is compute these optimal design things, which can be done in polytime, and run ridge regression.
Didn't we clarify what we mean by polytime before answering this question? So what is this a polynomial function of?
Oh, yeah, in that case, I think it would be a polynomial of the number of actions, d and h, which is length of the horizon. And I don't think this dependence on the number of actions is avoidable, because you need to enumerate these actions to say even maximize the linear function.
I guess, yeah. So without any extra structure, you just have to enumerate the actions for solving any of the the involved maximization problems. But the number of states also comes in because of the optimal design, which is a bit of a bummer.
Wait, why? It only does optimal design over the actions for this.
Oh, just the action part? Oh, okay.
Yeah, just the action part.
That's good. That's good.
Yeah.
All right.
Yeah. So it's only a polynomial of the number of actions.
Yeah. Okay, good. Yeah. So the only convenient part is that the number of actions shows up in the polytime result, but it's, I mean, you could miss what you have. Without further assumptions, you can't do better than that. But otherwise, it depends polynomially in dimension, horizon, that's it. Oh, inverse gap, I guess.
Right, you need to inverse for solving the ridge regression.
Sure, no, I was saying the 1 over data mean also comes into the polytime bound.
I don't think so.
But the algorithm needs to run for a while. Okay, like that's the
okay.
Complexity
that's true.
Or yeah, it's like this is the online sampling framework to come up with a good policy, and so the total runtime is going to depend on this inverse gap, of course.
Yeah, you're right, because the runtime is lower bounded by the sampling complexity.
So for the sparse, the sparse bias linear regression thing, so I guess like you introduce these assumptions, but the algorithm itself is just still doing like just ordinary linear regression, right?
Yes, the algorithm, the regression algorithm is the same. It's just ridge regression or ordinary least squares.
Right. Is there anything in the robust literature? Anyway, where maybe there's alternative algorithms or modifications to linear regression that helps us, maybe even further relax the assumptions, or are there any possibilities along those lines?
Yeah, we have considered this, but as for now, we didn't find those algorithms to be really helpful for us. One reason is that in the robust linear regression literature, they usually consider B as adversarial noise injected by an adversary. As in our case, it's more like oblivious. So they are considering an adaptive adversary, and often that adaptive adversary can even modify the X and not just tampering with the Y. And we consider an oblivious adversary that can only inject more random-like bias. So we just here we're just taking the hypercontractivity assumption, which in the robust linear regression literature is paired with a different algorithm to prove stronger results. and we use it to pair with these squares and get a weaker result, which is sufficient for us.
I missed the connection between this sparse bias regression and RL. Is it that the BIs are the places where the gap was insufficiently large? I missed just how it's the connection, I guess.
Yeah, I don't think that's very accurate. So the BI is non-zero when the agent takes an action that is non-optimal.
Okay, I see.
So basically, when you keep taking the optimal action, your estimate is unbiased.
Mm-hmm.
I had another question. Sorry if this was already covered, but I was wondering if you could give some intuition why where that gap assumption is used in the analysis.
Do you mean in the upper bound?
Yeah. Why do we need the gap assumption to begin with? Yeah, in the upper bound.
Yeah, that's a great question. So the reason is that the reason is that we want to convert a small loss in predicting Q star to a small probability of not taking the optimal action. So this is nice because if we can guarantee that we take the optimal action, except for a small probability, then apart from that small probability, you have no you're not suffering from any error. In the case where you don't have a gap, this error can be spread out in the sense that you keep making small errors. And this is actually worse for us because in this case, error is more prone to building up as shown in the lower bound example.
That makes sense, thanks. So we'll always have a gap with finite action spaces. So do we need to make some assumptions about having like a large gap? Or I guess maybe this is just another way of saying we have a unique optimal action. Is that correct?
You can think gap as a complexity measure. So if the gap is very small, then even in our case, the sample complexity bound can be exponentially large because our bound assumes that epsilon is smaller than 1 over c. So the final bound, smaller than 1 over delta. So the final bound actually has a dependence on 1 over delta min. So in the case where the minimum gap is exponentially small, our upper bound is also exponential.
Cool, that makes sense. Thank you so much.
Yeah, you're welcome.
The trivial improvement for this gap assumption would be that you don't need a small gap for states which are practically inaccessible.
Yeah, that could be one possible way for improving or relapsing the assumption.
But not much else can be done. Ideally, you would only want to say that I want a big gap wherever the optimal policy would go, but yeah, that may not be helpful at all. So maybe there is a lower bound even for the generative setting that would say that if you only assume that you have a big gap at states that the optimal policy hits with high probability, that doesn't have you.
Yeah, because the optimal policy may not be the most explorative policy in terms of covering all these directions. So in the exploration stage, you might come across these states with a very small gap.
Yeah, and since you don't know yet the optimal policy, it's kind of like a vicious circle, and that no algorithm can escape.
Yeah, exactly.
Yeah. That would be interesting to see, that lower bound. So obvious question, how you said about, so the upper bound is something constructive, but it seems to be very strongly tied to the finite horizon setting, the whole algorithm. Although maybe for discounting, you would say that like, let's just truncate. Is that going to work?
I think so. At least I don't think any particular reason why truncation would fail.
Oh, it's kind of tricky, isn't it?
Right. So what do you mean truncation? Truncation and then going back to some initial state distribution, or
yeah. So you have maybe a fixed initial state distribution like here, or even a fixed initial state, and you want to discover a good policy that is good from that initial state distribution.
So in a discounted model that you want to solve, what is the model of interaction? Are you still episodic, or you just keep playing the same trajectory indefinitely?
Yeah, so I allow you to like you can reset to the initial state distribution. That's fine.
If it's infinite horizon, then
it's infinite horizon, but you can reset. Like you use reset whenever you want.
Oh, okay. Then I voluntarily. Yeah, then I can set an edge to be, say, 1/1 minus gamma, and voluntarily reset after I reach this. I think the
gaps are going to change. Aren't they going to change if you do this? I
think the only thing that
if we had a big gap for the discounted setting, then we have a big gap even if you do this finite horizon approximation. Maybe even so. Is it obvious? We did. Is it also obvious that the functional approximation is going to work? We only assume that Q star is realizable. Like, how come that after the truncation, when you solve the finite horizon problem, then you still have realizability?
Yeah, that's right. So if it's only realizable in the original discounted case, then there will be approximation error after you truncate it.
Yeah.
So the question is then, how does our upper bound depend on this approximation error, which we haven't considered yet?
I think it's like, as long as root-D times the approximation error is smaller than the gap, then that would be fine. Because, that will be only amplified for one time, and that will be a root-D factor. So basically, root-D times the approximation error. I mean, as long as it's small enough, then.
But is it small? Like, do we know? Like, we have no prior way of doing this. Do we?
We take H large enough so that the.
But so when you go to the end, then you have this one-step problem, right? And then a two-step problem. Those value functions are completely different than the discounted value functions. The reasoning that they are close enough, it doesn't work anymore. So when you do the
but don't you have the, because of discounting, like when you convert it to the finite horizon problem, discounting will be baked into the reward function and value function themselves. So anything will be just close to zero there, right? And you have a, if you renormalize and ignore the discount factors, you have a large, huge approximation error. But because of like, gamma to the power of h, you just predicted whatever, like that should be fine. You just have a small approximation error.
So the induction, so you're saying that you pre-scale the rewards? Okay, so you introduce rewards which are not shared between the stages.
Yeah, I think everything has to be. Yeah, everything has to be time dependent after that conversion.
Should work. Okay. I buy it for now.
Yeah, I think the approximation error is actually the largest when at the middle. So I think it's gamma to a half of h.
Okay, interesting. Maybe.
Oh, by the way, I find it quite interesting when you have this gap separation between with the bilinear work, where whether you can query the feature of states that you haven't visited yet, like actually makes a big difference. I think that's kind of neat. Do we know other results of this kind before? Because usually it feels like, that kind of matters when you have some upper bound algorithms, want to use them, but sometimes it's unclear whether they actually make a difference.
Yeah, that's really, I think that's fascinating as well. So at first, I think one of these papers have to be retracted because
that was our initial thought. Something had one of the papers was definitely wrong, we thought.
Yeah, but in the end, it turns out that there's this very subtle difference in the setting, and that in the online setting, whether or not can you query a state that you're not currently at, or even a state that you cannot visit at all.
Yeah, so I think this is something like statistical rate versus running time trade-off. Right? Like basically, if you want to have a good statistical rate, then you must pay like large running time. This is actually pretty interesting, right? Like because we don't really know any this kind of result for other models.
We have a hard time hearing you.
Oh, sorry.
Ruosong.
Oh, I'm saying like this is like a statistical rate versus running time trade-off here, right? Basically, if you want to have good rate, then you must pay large running time because basically linear in S. Right? Because basically number of times you query features is a lower bound of the running time.
So I think this the reason that this setting matters is also has to do with the uniqueness of linear V star and Q star. So here you have two different systems of approximating, and the implicit step that their algorithm needs to do is to do a pruning in this hypothesis space of the V's and Q's that are not consistent in the sense that there's no action that makes the Q into this V. So it's this pruning step that requires the query of all the features.